Hello everyone and welcome to our project presentation. Our project is called Vertical Farm Aquaponic Greenhouse and it's basically use an automated aquaponic system. The main purpose of this system is to monitor water level and temperature automatically so we can maintain safe and healthy condition for the fish and plants. Normally, the problem of monitoring an aquaponic system manually is time consuming, inefficient and prone to human error. Also, the commercial monitoring system can be very expensive. So this project offers a cheapest and automatic solution for students or beginners. For platform, I use Tinkercad to make the wiring diagram. The system includes several actuators, such as a water pump, LED lights, and a buzzer to alert when conditions are unsafe. The main objective are to use C++ programming to read the water level and temperature, and to automatically control the pump, LEDs, and buzzer based on the sensor value. We also create a flowchart, wiring diagram, and a complete simulation to show how the system operates. Overall, this project shows how automation can make aquaponic farming easier, safe, and more efficient.
This flowchart represents the full operation of an aquaponic water level and temperature monitoring system. The system begins with initialization where all pin modes are configured, serial communication starts, and the pump is turned off for safety. After setup, the system enters a continuous loop every 2 seconds and the Arduino reads both the water level and the temperature. The ultrasonic sensor measures the distance to determine the tank's water level, while the TMP36 sensor measures the water temperature. These values are then displayed on the serial monitor so the user can see the current status. Next, the water level is evaluated. If the distance shows full, optimal, or low, the pump stays off and the appropriate LED lights up. But if the level becomes critical, the pump turns on and a buzzer alert is activated to indicate that water needs to be added. After that, the system checks if the pump is currently running and whether the water has reached the optimal level. If so, the pump automatically switches off. After that, the temperature is then classified into too cold, too hot, or normal ranges. For unsafe temperatures, the system triggers warning using the red LED and buzzer. For safe temperatures, the warnings are cleared. Finally, the system returns to the main loop and repeats the process continuously, ensuring constant monitoring and control.
Good day, doctor. My name is Dharmendra Sivasubramaniam. Let's now look at the heart of our system, the input and output components, also known as the IOLIS table. This table maps out exactly how our aquaponic monitoring system is wired together. Starting with the inputs, which are our sensors, we have the ultrasonic sensors, which is split into two parts on the table. Pin 10 is an output from the Arduino that sends a trigger signal to the sensor. Pin 9 is an input that listens to the returning echoes. Together, they calculate the water level by measuring the distance. The temperature sensor is connected to analog pin A0. It continuously reads the water temperature by sending a variable voltage signal to the Arduino. Now, for the outputs, which are our actuators and indicators. We have a set of 3 LEDs that act as a visual status indicator. The green LED on pin 4 lights up when the water level is optimal. The yellow LED on pin 3 provides an early warning for a low water level. And the red LED on pin 2 activates for any critical condition like a very low water level or a dangerous temperature. The buzzer on digital pin 5 provides an audible alarm to accompany the LED red, ensuring the alert is noticed. Finally, the most critical output is SPDT relay on pin 7. This acts as a smart switch, allowing the low-powered Arduino to safely turn the high-power water pump on and off to automatically refill the tank when needed. The I/O configuration forms the complete control loop. The sensors feed data in, the Arduino's code makes a decision, and the lights, buzzer, and pump carry the action out. Thank you.
Now, I will explain the coding for setup and initialization of automated aquaponic system. First, we use const_in to define pin numbers that doesn't change, like sensor, LEDs, and pump. Next, for const_float is used for temperature threshold because it can have the decimal. And for variable like long duration, in distance, and float temperature is basically store sensor data. While bull pump active is track if the pump is on or off. Unsigned long last read time and read interval is control how often the system take reading. The void setup is function to run once at the start. For serial begin is allow us to see data on serial monitor. The pin mode function is to set each pin as input or output, depends on whether it's receive or send signal. Next, I will explain the system timing and integration. In the void loop, the system runs continuously to keep checking the water level and temperature. First, we get the current time using release, and we only take a new reading when enough time has passed. This check using if current time last read time read interval. Then we update the timer and read the sensor. Distance measure water level and temperature measure temperature. Next, we show the reading using display water level and display temperature. After that, the system make the decision. Control system distance decide if the pump should turn on or off, and check temperature is check if the temperature is safe. This repeat and non-stop so the aquaponic system stay update in real time.
Now, let's look at the code that brings our sensors to life. First, for water level measurement, we use the measure water level function. The Arduino sends a precise 10 microsecond trigger pulse to the ultrasonic sensor. Then it listens for the echo and calculates the distance based on how long the sound takes to travel back. As you can see in the code, the calculation is straightforward. We convert the pulse duration into centimeters. This gives us a real-time, non-contact measurement of the water level. For temperature monitoring, the measure temperature function reads the analog voltage from the temperature sensor, TMP36 sensor. The code converts the raw sensor reading into a voltage and then applies the sensor's specific formula to get the temperature in Celsius. The temperature sensor's outputs 10 millivolts per degree with a 500 millivolt offset at 0 degrees Celsius. These two functions are the foundation of our monitoring system, providing the critical data that drives all our automated decisions. Thank you.
For my part of the project, I was responsible for creating the serial display output functions which show the water level status and temperature status on the serial monitor. First is the water level display. This function prints the measured distance from the ultrasonic sensor and converts it into an easy to understand status. The reason for using multiple if-else conditions is to categorize the tank condition clearly into full for overflow risk, optimal for ideal water level, low for early warning, and critical for pump activation needed. This structure output helps the user immediately know the tank situation without manually checking the sensor values. And next is for the temperature display. This function reads the temperature in degrees Celsius and matches it against safe ranges for fish. The conditions ensure clear communication of too cold, optimal, warm, and too hot. These messages are important because fish survival depends heavily on maintaining a stable temperature. The reason these functions are designed this way is to provide simple, readable, and real-time feedback to the user. Instead of raw numbers, the system gives meaningful labels, meaning the aquaponics system is more user-friendly.
Let me now explain the control system function, which is my contribute in these projects. This single function manages all the system output, the 3 LED, the buzzer, the pumps, which is based on the water level readings. Here how it makes the decisions. Why we need this function? This function eliminates manual monitoring by automatically taking water every 2 seconds and taking immediately action to protect the fish and equipment. How it works? The function starts by turning off all the LED and the buzzer to clear any previous stage. Then it uses a cascaded if-else structure to evaluate 4 different water level conditions in order. First, if the distance is 10 cm or less, the water is too high and approaching the overflow. The system turns on the red LED and clips the buzzer and keep the pumps off to prevent the flooding. Second, if the distance between 11 and 20 cm, this is optimal conditions. The green LED will on and show everything is fine, and the pump stay off because no action is needed. Third, if the distance is between 21 and 25 cm, we are in the warning zone. So yellow LED active to alert us that the water is getting low, but the pump still does not turn on because it's not yet emergency. Fourth, if the distance exceeds 25 cm, this is critical water level. So the red LED will turn on and the buzzer will sound longer alerts, and most importantly, the pumps automatically on and start to refilling the tank. Finally, there are smart safety feature at the end. The function check if the pump is running and if the water was returned to the optimal level. If both are true, and the pump will automatically off to prevent the floodings. This demonstrates intelligence automatics because the system knows when to start without human intervention. Let me explain the check temperature function, which is also my contribution to our project. While the control system handles the water level, this function only monitors the temperature to ensure the water stay within the safe range for the fish health. This function receives the current temperature reading as a parameter called temps. It's then checked whenever this temperature falls outside our safe range, which we define as 20 to 30 Celsius. The first condition uses OR operator to check if the temperature is either too cold or less than minimum 20 Celsius or too hot greater than the maximum of 13 degrees. If either condition is true, it means we have a temperature problem, so the function set the temps warning flags to true. This function then checks if the water level is currently optimal, meaning the distance is between the full and optimal thresholds. This is important because we don't want the temperature warning to interfere if there are already critical water level problems being handled. If the water level is fine, the function takes an action. It first turns off the green and yellow LED to clear any previous stage, then turn on the red LED to indicate the danger, and activate the buzzer beeps with the minimum pitch beeps at 1500 Hz to 115 milliseconds. This creates a distinct sound that different from the water level alert. Next, the function provides specific feedback through the serial monitor. If the temperature is below minimums, it prints temps warnings, water is too cold, consider adding heater. But if it above maximum, it prints temps warnings, water is too hot, improve ventilation or cooling. This message not only alert the user, but also suggests the corrective actions. If the temperature is within the safe range, then else block simply set the temps warning it to false, indicated there is no temperature problems. Finally, the function prints a separated line to make the serial output easier to read. I will demonstrate our aquaponic monitoring system that automatically control water level and temperature for fish health. As you can see on the screen, you guys can refer to the bottom right, which shows serial monitor. Then we have a result, so I will explain according to the result. First, normal operation, which is optimal, water level at 18 cm, temperature at 24.7, and the green LED on that shows everything's on optimal conditions, and action pump off, red and yellow LED off is needed. So this is our baseline. For a second condition, which is critical water level, while the temperature is still on optimal condition, which is 24, but the water dropped to 13 cm, which is critical and need to adding the water. So the system will show you that red LED on, while the other LED turn off, and the buzzer beeps at 1000 Hz, and then action is the pumps on, and the system will automatically human intervention needed. The third condition is temperature warning, which our water level returned to 18 cm, but the temperature rise to 33.09 Celsius, which is above our 13 Celsius is the maximum. So the system will show you that red LED on and buzzer will beep at 1500 Hz being activated, and the pump will stay off since the water level is on the optimal conditions, but the high temperature depletes oxygen and stresses the fish, so the system will alert immediately. The scenario is water at 31 cm and the temperature is still the same, which is 33.09 Celsius. The red LED ons and buzzer. The system handle both problems, where it can activate the pump for the water while alerting about the temperature. Not confused, proper respond to the multiple.
For conclusion, first, automatic aquaponic system achieved. This means our system can automatically monitor water level and temperature without us doing anything manually. Based on the sensor reading, the system will control water pump on or off, change the LED indicators, and activate the buzzer if they are running. So the whole aquaponic system can run safely and consistent on its own. Second, technical integration. This point shows all the components are successfully connected and programmed. We use the Arduino Uno R3 as the main controller, the HC SR04 to measure the water level, the PMP36 to measure the temperature, and the relay module control the water pump. The LEDs and buzzer provide visual sounds alert, so all these parts work together as one system. Third is simulation and programming. For this project, we did not just coding, we follow a full system documentation. We create flowchart to plan the logic, design the wiring diagram in Tinkercad, listed all input and output device, and write a complete C++ program. Finally, we test everything in Tinkercad to make sure the system works correctly. Fourth is skill and learning. Throughout this project, we gain hands-on experience using C++ programming to control real hardware in its embedded system. We learn how to structure programming is used in engineering, how sensor and actuator communicate with the Arduino, and how to create an embedded control system. These skills are very useful for future engineering projects and real-world automation system.